Okay, so thanks to Thomas and the other organisers of this programme. First off, I'm going to apologise for not being there in person. If you might have just caught me moaning, I have experienced some bureaucratic issues that have prevented me from travelling. But nevertheless, it's I'm very happy that the organisers have allowed me to give this talk remotely. So I'm very grateful to them. So I'm going to present some work which is joint with my colleague Jim Wright here in Edinburgh. And yes, so in particular, I'm going to discuss some very recent results on kind of Littlewood-Paley or square function inequalities for curves. So I'm going to begin by introducing the basic setup and motivating these problems. So we're going to work with gamma, which is a parameterization of the moment curve. So this is the curve whose components are given by the first n monomials, t squared up to tn. We're only interested in a compact portion of this curve, so we're going to restrict this parameterization to this unit interval. So we'll let delta be some small parameter, and we're going to consider functions f, which are Fourier supported in a delta to the n neighbourhood of this moment curve. So you see here in the picture, we've got this blue curve, and then we've got this green tubular region around it, and our functions have Fourier support in this set. So this kind of situation arises in a variety of contexts, particularly in relation to some questions in analytic number theory, which I'll kind of hint at later on. And typically when you have a function with this Fourier support, it's quite hard to analyze, and that's due to the fact that its curve is highly non-convex. The Fourier transform behaves well with convex objects. So one thing we can try to do is to break this up into smaller pieces. So hopefully these smaller pieces are easier to understand. So in view of this, I'm going to partition the parameterizing unit interval into small delta intervals. And this partition is going to induce a partition of our supporting set. And consequently a partition of our function. So we'll write f as the sum of pieces fi, which are frequency localized. They're parameterized by these intervals I, and each fi is Fourier supported in the delta neighborhood of the portion of the curve over the interval I. Okay, so we've broken up into these pieces that have support in these little sections of the tube, which have length delta and width delta to the n. Okay. Are there any questions about this? Okay, so that's our basic setup. So the fundamental problem we're interested in is to compare our original function f in size, magnitude, with these localized pieces fi. And well, there's an easy bound for doing this, and that's just to apply the triangle inequality, and which gives us a pointwise comparison. However, this is somewhat naive, and the reason for that is, well, by definition, each of these fi have disjoint frequency supports, so they're all going to oscillate with different frequencies. So we're going to expect cancellation between the terms in the sum. We're going to expect a lot of destructive interference in general, and morally, what we tend to expect in this situation is a square root cancellation. So we should be able to upgrade the little L1 expression on the right-hand side of the triangle inequality with some kind of little L2 expression. So this is morally what should happen as an effect of this cancellation. So this kind of pointwise estimate is a little bit naive, and it doesn't hold in general. But we can formulate this kind of behavior precisely, and here are two ways of doing this. So the classical approach to this kind of phenomenon is through a square function bound, where we show that this little L2 sum dominates the function, not pointwise, but on average in terms of the LP norm. Okay, so we get some kind of LP norm inequality of this form, and this is an instance of a Littlewood-Paley inequality. And then there's the kind of more recent variant of this, which are these decoupling inequalities, which have been proved to be a very successful tool in analysis. And they take roughly the same form, except we interchange the order of the little L2 and little L2 and big LP norms on the right-hand side. Okay. So we don't have these estimates for all P, they hold for a restricted range. So in the for the square function bound, this holds for all P between 2 and 2n, provided you interpret this this suppressed constant in a suitable manner. And so this kind of bound, well, it kind of dates back to work from the pioneering work of Hickman and Cordoba from the 1970s, but it was discussed and investigated in detail in a recent paper of Gressman, Guo, Pierce, Roos, and Young, which I'll refer back to. Although these kind of estimates kind of do appear implicitly in early work of Prestini from the 80s. On the other side of things, the decoupling inequality, well, maybe I should mention, whenever we have a square function bound, we automatically have a decoupling inequality just by applying Minkowski's inequality to interchange these norms. However, the raison d'etre for these decoupling inequalities is that although they're weaker for a given P, they hold for a larger range of P. So we can push this all the way up to n times n plus 1. And this is this the celebrated Bogan-Demeter-Guth theorem, which has had a well, kind of startling impact on analytic number theory. So I want to mention in passing the connection between these decoupling inequalities and number theoretic problems. So this is very well known, but it kind of helps to contextualize what comes later on. So this Bogan-Demeter-Guth decoupling inequality kind of quite directly implies what's known as the main conjecture in Vinogradov's mean value theorem. So this main conjecture involves counting integer solutions to a system of power sums. So this is a question in Diophantine equations. It's perhaps of interest in its own right, but primarily interest in this problem relates to Vinogradov's method for studying the wearing problem. And it turned out that understanding the precise count for the solutions to this system of equations was a major stumbling block in analytic number theory for many decades. So it turns out for this problem, the critical case is when the number of variables, which here is 2s, is equal to n times n plus 1. And once you understand the solution count for this special case, you can deduce the number of solutions in other for other parameters by elementary means. So this n times n plus 1 corresponds to the numerology in the Bogan-Demeter-Guth theorem. It's the same as this endpoint exponent for the decoupling. And the fact that you can go all the way up to n times n plus 1 with these decoupling inequalities is crucial for this application to the Vinogradov mean value theorem. Okay, and it's the reason why the decoupling inequalities are the kind of correct tool for these problems, as opposed to the stronger square function bounds, which only hold in a restricted range. Okay. Any questions about this? Okay, so although the square functions aren't kind of, well, don't tell you anything about the Vinogradov mean value theorem, there nevertheless are some connections between these estimates and problems in number theory, and these connections were investigated in the recent paper of Gressman and co-authors, which I mentioned on the earlier slide. But here the implication is reversed. So in particular, they observed that you can deduce the square function bounds as a consequence of a count on what I'll refer to as approximate solutions to a Vinogradov type system of equations, so a system involving power sums. Okay, so this observation is, well, it's really kind of based on the tools that have been around since the 70s of Cordoba and Hickman, and uses kind of higher order, what I'll call higher order orthogonality argument. And but it's quite nice to kind of contextualize these methods in terms of these recent developments in analytic number theory. So this is kind of the starting point for the investigations I want to discuss in this talk. So I'm going to take a little bit of time to kind of illustrate how we can relate these square function bounds to these approximate solutions to systems of equations, and what it means to be an approximate solution to a system of equations in this context. Okay, so I want to kind of to paint the picture behind this implication. So these square function estimates are always trivial when p is equal to 2. They just follow as a consequence of Poincarel's theorem. So so what we're going to do is we're going to shoot for the other extreme when p is equal to 2n. So this is kind of the endpoint exponent for these estimates. As a slight caveat, I should mention that there's no standard interpolation theory for these kind of square functions. So if you want to get an estimate for an intermediate range of p, you have to work a little bit harder than usual and use alternative means. But we'll just focus on this 2n exponent. And here we're going to heavily exploit the fact that 2n is an even integer. And this will allow us to use a whole bunch of Fourier analytic tools. So let's just go through the rudiments of this Cordoff and Pfefferman argument. So it's based on using orthogonality, Poincarel's theorem. So I'm going to take the L2n norm of the function, which is what the quantity appearing on the left-hand side of the desired inequality. We'll raise this to the power of 2n, and then I will write the function in terms of its decomposition into these frequency localized pieces. I'm also going to do some gymnastics with the exponents. So I'll write the 2n power the absolute value as the absolute power value, the nth power squared. Okay, so and once we do this, I'm just going to expand out the square of the absolute value as the product of the complex number and its conjugate. So that's here. So the next step is simply to expand out these the products of the sums as the sums of products. So once you do the algebra, you end up and pull out the summation, you end up with the sum over all pairs of n tuples of intervals I1 up to In and J1 up to Jn, where we're integrating these L2 inner products of a left function and a right function. The left function is just the product of fi1 up to fin, and the right function is just the product of fj1 up to fjn. Okay. So now, well, this has all just been algebra. So now we apply some Fourier analysis in the form of the Parseval identity, which allows us to write the inner product of the two functions as the inner product of the Fourier transforms. And when we take the Fourier transforms, well, the left function becomes the n-fold convolution of the Fourier transforms of the fi, and the right function becomes the n-fold convolution of the Fourier transforms of the fj's. Okay. So all very elementary. So I'm carrying over this highlighted expression is just the statement we conclusion of the last slide. So now I'm going to home in on one of the terms, call it Sij. And of course, this Sij will contribute to the sum in the sense that it's non-zero, only if the support of the two functions is the two functions in their product intersect. Okay, so we want to now analyze the supports of these n-fold convolutions. So of course, the support of the convolution is contained in the Minkowski sum of the supports. So if the Sij contribute to the sum, then we must have the intersection between these two Minkowski sums. Okay, so this is kind of the key observation here. And what we'll show is that this doesn't happen very often. So for a typical choice of intervals I1 up to In and J1 up to Jn, these Minkowski sums will have disjoint support. Okay, and so only very few of the terms in the highlighted expression will contribute to the sum. So more explicitly, we have this kind of morally, this is the statement that holds. So this isn't quite true, but up to kind of constants it is. So one trivial case where these Minkowski sums do intersect is when the J's are just formed by some permutation of the I's. Okay, so of course then the two sets are identical. And it turns out that essentially this is the only case in which they intersect. Okay, so so only the trivial situation counts somehow. So this turns out to be the key observation in this whole argument. But for now, I'm just going to assume that we know this. And what we can do is, well, if we go back to our expression from the earlier slide, we see that only the diagonal terms in this sum survive. So by diagonal terms, I mean the terms exactly when the J's are formed by a permutation of the I's. Okay, so if we take account of this, well, we can introduce an n factorial factor to count the number of permutations, and then we're left with the inner product of we can remove the sums in the J's, and for each n tuple of I's, well, we're left with the inner product of the left function with itself. Okay, so we can write this inner product as an L2 norm, and at this point we just kind of reverse all the steps from earlier in the proof. So in particular, we take these L2 norms, we apply Plancherel to go back to this physical domain, and the n-fold convolution goes back to being an n-fold product. We then interchange the order of summation and integration and write the sum of the products as a product of sums. And lo and behold, we arrive at the desired expression on the right-hand side, this L2n norm of the square function. Okay. So that's the simple scheme in order to prove these square function bounds. Of course, it's very elementary, but the proof boils down to showing this geometric property about the supports of the Fourier supports of these functions. Okay. So does this make sense? Are there any questions? Okie dokie. So I want to investigate this support property in a little bit more detail because it's the linchpin of the whole proof. So let's remember that these localized pieces, the FIs, are Fourier supported in a delta the n neighborhood of the portion of the curve over the interval I. So this means if XE lies in the support, then there must exist some point S in the interval such that the distance between XE and gamma S is at most delta to the n. Okay. So if we have a point XE that lies in the Minkowski sum of these supports, then there must exist a whole bunch of points Sj for each ij going from 1 to n, such that the different distance between XE and the sum of the gamma Sj's is at most delta to the n. Okay. So this is just unraveling the kind of definitions in the setup. So now let's suppose that these two sets intersect, these two Minkowski sums intersect. So we can apply the observations of the previous slide together with the triangle inequality and deduce that there must exist points Sj lying in the respective I intervals and points Tj lying in the respective j intervals, such that if we form the sum of gamma Sj and the sum of gamma Tj, well, the difference between these two sums is bounded by delta to the n. So whenever these Minkowski sums intersect, we can deduce that there exists the S's and T's with this property. So I just want to recall that we're working with the moment curve here. So the components are given by these monomials. So if we look at this condition between the differences of the sums of the gamma Sj's and gamma Tj's, then, well, we can write this out explicitly in terms of each of the components. And we see that the S and T form an approximate solution to a Vinogradov type system. And what I mean here is, well, they satisfy this Vinogradov system consisting of power sums up to some small error term, okay? And the error term has size of delta to the n, okay? So this will be what we mean by an approximate solution. Now, the key proposition kind of characterizes these approximate solutions to this system. So this is the key ingredient in the paper of Gressman and co-authors. So let's suppose that S and T are an approximate solution to our Vinogradov type system in the sense that we described earlier. So if we look at the difference between the kth power sum in S and the kth power sum in T, this is at most delta to the n. Well, then this solution must be almost or approximately trivial in the sense that the T's are formed by some kind of, are approximately given by a permutation of the S's. So more precisely, we can conclude that there exists a permutation sigma such that the difference between Tj and S sigma j is always less than delta in absolute value. So once you have this, this characterization of these approximate solutions, you can go back and feed it into the argument, and you can establish the desired kind of support property for these Minkowski sums of the supports. And that is the missing ingredient which allows you to complete the proof of the square function bound. So the whole thing hinges on this kind of, well, somewhat number theoretic statement about characterizing approximate solutions to these system of equations. Any questions? Okay, so so far I've just really described what observations in this paper of Gressman and co-authors. So I think it's high time to explain some new results. So our perspective on this problem is the following. So given these natural connections between square functions and decoupling and problems in Diophantine equations, it's perhaps natural to explore these harmonic analysis problems in other settings which are of interest in number theory. So the settings we have in mind are the p-adic integers and rings of congruence classes Z mod p to the alpha. So Jim and I have thought about harmonic analysis in these kind of contexts for a few years now, but we were inspired to at least partly inspired to consider these square function problems by a recent paper of Biggs, Brandis and Hughes, which indeed look at these square functions over the p-adics, amongst other things, but only in the two-dimensional case. Okay, so their work is only restricted to 2 dimensions, and we wanted to understand what happens in higher dimensions to some extent. So before moving on, I should reassure everyone that, well, in the spaces that we have in mind, there is a well-developed Fourier analysis we're always working on for a locally compact abelian group. So the questions we're asking about these square functions at least make sense in these contexts, so you can formulate these problems rather naturally. Moreover, we have access to tools such as Parseval's identity, Plancherel's theorem, etc., and all the Fourier analytic aspects of the argument kind of carry over wholesale into the p-adics, into these rings of congruence classes. Okay, so the Fourier analytic aspects of these arguments don't present any interesting new challenges. But one crucial difference in working over these settings is the lack of order structure. So the real line is of course like has this total order, and which is kind of a characterizing property of the field. And with this comes a lot of the familiar tools from calculus, such as intermediate value theorem, mean value theorem, etc. So all these tools kind of essentially become unavailable when we work in these settings that we have in mind. And therein lies the key difficulty in the extensions that we're trying to prove, because these tools from calculus play a heavy role in the proof of the central proposition about characterizing these approximate solutions to the system of equations. So the arguments of Gressman and co-authors use a lot of tools from calculus. They use and kind of intermediate value theorem. So we can't carry over the proof of this proposition into the p-adic setting, for instance. Okay, so because this number theoretic proposition kind of is the source of the main difficulties and the extensions that we're interested in, I'm going to focus just on describing how this central proposition works in these other settings. So here I'm going to look at the ring of congruence classes mod p to the alpha. So we'll pick a prime p which is bigger than n, so we have to enforce this condition to avoid certain degenerate situations. It's kind of natural for this kind of problem. So we'll suppose now that S1 up to Sn and T1 up to Tn are n tuples of integers which satisfy some system of congruence equations. So in particular, we have exactly the same system of equations as before, these first n power sums, but now we're asking the kth power sum in S to be congruent to the kth power sum in T modulo p to the n alpha. Okay. So this will be our analog of an approximate solution in this setting. So we're not asking the integer it to be a true integer solution, but it to hold up to some modulo some relatively large power of p. And our conclusion is that this approximate solution has to be approximately trivial as before. So in particular, up to permutations, the tj's are congruent to the sj's modulo p to the alpha. Okay, so the tj's don't have to be exactly equal to the sj's, but at least modulo some prime power, they are equal. Okay. So this proposition can be used to prove a square function bound over these discrete rings of congruence classes using exactly the same argument as I showed earlier. So I'm not going to focus on the Fourier analytic proofs, Fourier analytic arguments from now on. And also it can be used to prove a result over the p-adic numbers. Actually, we will focus on the p-adic numbers kind of later on. So the proof is very different from that used in the real case by Gressman and co-authors. And as I mentioned, it kind of necessarily has to be quite different because the proof of Gressman et al. Uses heavily the order structure of the real line. And in fact, our arguments give a kind of, in some ways, a unifying approach because you can adapt them also to work in the Euclidean case and recover the theorem of Gressman and et al. For at least in this moment curve case. And although carrying out these arguments in the Euclidean setting is a little bit messy, so adapting the argument requires a little bit of work. Are there any questions about this statement? Okay, so it turns out that it's kind of convenient and also necessary for our analysis to actually work over the p-adics rather than these rings of congruence classes. So I appreciate that not everybody in the audience might be familiar with p-adic analysis, but I'll give the statement, and then for the purpose of the rest of the talk, we can kind of pretend we're working over the real line, essentially. So when we're working over the p-adics, the key proposition looks very similar to the Euclidean case. We now have an approximate solution which is defined in terms of the p-adic norm. So the p-adic difference between the kth power sum and the s's and the kth power sum and the t's is bounded above by p to the minus alpha n here. And then the conclusion is we have an approximate solution, which again looks very similar to the conclusion in the Euclidean case. Okay, now working with this p-adic norm rather than the usual Euclidean norm. So I'm gonna kind of discuss how we go about proving this statement in the p-adics. But like I was saying, for the purposes of talk, we can just think of the p-adics as, say, the unit ball in Euclidean space as a metric space. Okay, and but there are two things, at least two things which we'll use about the p-adics. So first of all, this p-adic norm is a little bit weird. It satisfies what's known as the ultrametric triangle inequality. So we can upgrade the right-hand side of the triangle inequality to a maximum, basically. And what this means is that when you're working over the p-adic setting, well, first of all, the triangle inequality tends to be a lot cleaner. We lose a lot of constants that usually come up in triangle inequality arguments. But more significantly, the balls in this p-adic space behave like dyadic intervals in the real line. Okay, they have kind of the basic covering properties of dyadic intervals. Oh, yeah.
Sorry, can I quickly ask, what is the difference between this proposition and the proposition on the previous slide?
They're completely equivalent.
Okay, thanks.
But I will need to work with the p-adic set. So basically, my motivation for stating the first one is because I'm pretty sure everybody's familiar with congruence classes, but I'm not sure everyone's familiar with p-adic analysis. But I will have to use a p-adic analysis to describe the proof. Does that make sense? However, we can pretend basically in the p-adic case we're working over the real line. We're just going to use some simple properties of the metric that are special to the p-adic metric.
Okay.
Okay. So we have this ultrametric, which means that the balls behave like dyadic intervals, and also the norm only takes a discrete range of values. So in particular, if we have a non-zero element in the p-adic numbers, then its norm is of the form p to the minus nu for some non-negative integer nu. Okay. So these are two facts we'll have to bear in mind. So for the final part of this talk, I want to discuss a little bit about the proof scheme. So this the argument is quite algebraic. I want to give some flavor of the kind of tools we use, without maybe going into a huge amount of detail. So let's suppose we have a approximate solution to our system of equations. So our original system of equations is formed by these power sums. So I'm going to let pk denote the kth power sum. And if S and T form an approximate solution, that means that the power sum of S minus the kth power sum in T is in absolute value at most p to the minus alpha n. So this is our hypothesis. So we have this approximate solution. So the first observation, which is kind of fairly standard, is to see that this S and T is also an approximate solution for a different system of equations formed by elementary symmetric polynomials. So in particular, I'm going to let EK denote the kth elementary symmetric polynomial, and we can relate the EKs to the PIs through some very classical identities called the Girard-Newton identities. And by doing this, we can see that the S and T must also be an approximate solution to this system of equations formed by the elementary symmetric polynomials. Okay, so we pass from one system to another. Now, the second part of the proof is to use the fact that the elementary symmetric polynomials appear in the expression for relating the coefficients of a polynomial to its roots. So in particular here, I'm letting f of fxe be the polynomial with roots xej. And then, of course, we can expand out this product and write the resulting expression in terms of the elementary symmetric polynomials. Now, let's remember from the previous slide that our approximate solution is an approximate solution to this system of differences of elementary symmetric polynomials. And as a consequence, if we look at the polynomial with roots given by the S and the polynomial with roots given by the T, then these polynomials have coefficients which are very close to one another. Okay? So since the coefficients of these two polynomials are very close, at least if we evaluate this polynomial over the unit ball, and we can think of the p-adics as being the unit ball, then the values of these polynomials must be close. So in particular, this difference between fs of z and ft of z is at most p to the minus n alpha in p-adic absolute value. Okay, so whenever f of s is small, f of t is small, and vice versa. So because of this, we can identify the sublevel sets of these two polynomials. And in particular, if we look at the sublevel set at height p to the minus n alpha of f of s, this is exactly the sublevel set of f of t at the same height. And this is the kind of starting point of our whole analysis, and the rest of the argument is going to rely on analysing these sublevel sets. Okay, so at this point, I want to take stock of what we've done and observe that we have at least we've already made some partial progress on the problem. So remember, the tj's are by definition the roots of the polynomial ft. Okay, so the tj's must necessarily lie in any sublevel set, okay, because these are the points where this polynomial vanishes. So because the sublevel sets are identical, we know that the tj's must lie in the sublevel sets of the fs, okay? So we can just unwrap the definition, and this means if we evaluate fs at tj, then the polynomial is less than p to the minus n alpha in absolute value. So if we write down the definition of the polynomial, this means this product of the difference between our fixed tj and the si's is bounded by p to the minus n alpha. Now, because there are n factors in this product, we immediately observe that there must be some index, let's call it sigma j, such that tj is close to sigma j. So tj is the difference between tj and sigma j, and absolute value is less than p to the minus alpha. Okay, so here we see this relationship between the two scales, p to the minus n alpha and p to the minus alpha, playing a role. So this is some partial progress, because we can at least say the roots of the tj must be close to the roots of the sj, but it's not enough for our purposes because we need a bijection between the two families of roots, and this turns out to be the main difficulty in the argument, establishing the existence of a bijection. So of course, one enemy could be if many of the tj cluster around an isolated si. So many tj are just close to a single si, and then we wouldn't have a bijection. So we kind of have to rule out this enemy case, which means that we have to show that the two families of roots are kind of similarly distributed, they're spread around in a similar way. So in order to get this bijection property, we have to carry out a fairly detailed structural analysis of these sublevel sets. And this relies on what is a very elementary, but I think we have a beautiful lemma, which comes from the work of Fong, Stein, and Sturm, and is adapted to this kind of context in works of Jim Wright. So this says, if we have a polynomial fxe with distinct roots xe1 up to xen, then we can write the sublevel set as a union of balls, each centered around one of the roots xej. And moreover, we can obtain a nice expression for the radii of these balls. So the radius of the jth ball is given by, well, okay, we have this explicit expression here. So unfortunately, I'm running a little bit low on time. So I will kind of skip over, well, I won't describe in detail what this, the motivation behind this expression, except to say that it involves the distance between the xej, the fixed root, and the other roots of the polynomial, okay? So the radii can be explicitly written in terms of the distance of our fixed root to all the other roots of the polynomial. Okay, so the next step is to apply this this decomposition of the sublevel set in our situation. So we know that the sublevel set of the polynomial with the roots given by the SJs can be written as a union of balls, and similarly for the polynomial whose roots are given by the TJs. And we know that the sublevel sets are identical, so we can identify these union of balls. Okay, so we have two families of n balls now, and we know that they're union, so the same set. So at this point, we're going to apply the Vitali covering lemma in this ultrametric setting to pass to a disjoint family of balls. Now, as I said, the balls in the p-adics behave like dyadic intervals. So this is just like the dyadic Vitali. We pass to the maximal balls with respect to inclusion. And once you do this, well, it's quite clear that in the number of maximal balls for the SJs is equal to the number of maximal balls for the TJs, and moreover, there is a bijection between we can identify the maximal balls of the SJs with maximal balls of the TJs. Okay. So after relabeling, we can identify these balls as highlighted here. Now, in the Euclidean case, identity of balls implies identity of radii. And we'd like to deduce the same thing in the p-adic setting and conclude that these radii have to be identical. Now, it turns out that there's a subtlety here, and this relates to the fact that the p-adic norm only takes a discrete set of values. So we can't deduce this implication directly in the p-adic setting. And so to get around this, we actually have to work in a variety of other fields. And in particular, we work with a high degree field extension over the p-adics. And this field extension has an absolute value, which takes a richer range, which kind of allows us to get around this problem. So in some sense, this is a bit of a technicality, but in another sense, I thought I'd mention it because it's kind of curious feature of the argument that in order to prove this result of the p-adics, we have to make use of the analysis of this polynomial over high degree field extensions. Okay, so I think, I'm just going to wrap things up. So once we have identified the radii of these balls in the sublevel set decomposition, we can apply the explicit formula from the Fungstein-Sturm lemma. And this allows us to identify these expressions which involve the separation of the roots. So now we're going to have another system of equations which involves these separations of the roots. And what we can show is that these equations can only be satisfied if the SIs and TJs are similarly distributed. So this is perhaps intuitive because we see that these quantities that involve the root separations have to be identical. And it turns out that this can only happen if the SIs and TJs have a similar distribution. And this allows us to, so this takes a little bit of, well, you have to play around with the algebra a little bit, but one can deduce this. So in particular, this rules out this enemy scenario where for instance, we have one isolated SI that is close to many TJs, because this identity between the radii would preclude this from happening. So this kind of concludes the proof of our argument. So I'd kind of like to mention that as I said, we can adapt this to work in the Euclidean case, but it turns out there are some complications, particularly around the use of this ultrametric Vitali lemma. But you can get around this. It just involves some technicalities. So this, and also this proof of the Fungstein-Sturm, the use of this Fungstein-Sturm thing in this context is kind of quite interesting, because it gives access to this very precise description of the sublevel set seems to be quite powerful. And we have various other additional applications of this lemma in mind for other problems related to harmonic analysis and number theory. So it seems like this is quite a useful tool in this context. So that's everything I have to say. Thanks for your attention.